I'll be happy to open this special meeting of the Con Research Seminar, which is also a Bar Hillel colloquium in collaboration with the Hebrew University Edelstein Center and the Van Leer Institute of Jerusalem. And we have a special guest, Professor Bernadette Bensaude-Vincent, which unfortunately we can meet only through the Zoom and not as planned in flesh. But as you know, it's difficult to plan things these days. So we hope to. We think it's better to have it in this way as to cancel the talk at all. And so Professor Bensaude-Vincent, she's a philosopher and historian of science. She's a Emerita professor at University Paris 1 at Sorbonne. She completed her PhD in philosophy at the same university and taught history and philosophy of science at the University of Paris Nantes until 2009, and from 2010 she's at Paris 1. She was a guest professor at many places, which I won't mention all of them. The number is quite high, and she got many rewards. I will mention the most important of them, or those who jump to my eyes. She's a member of the French Academy of Technology and a number of ethics committees in France. She received the Dexter Award for Outstanding Achievement in the History of Chemistry, which is from the American Chemical Society. And just recently, a few weeks ago, she was awarded the History of Science Society's 2021 Sarton Medal, which is the highest distinction that the History of Science Society gives to its members. Actually, it's not. For historians of science, they don't have to be members. I guess most of them were. And her research topics span from the history of philosophy, of chemistry, to material science and nanotechnologies, with a continuous interest in science and publications and the public issues. She also worked on history of physics. She gave quite a few. She mentioned in her short bio a few publications. I would mention one more, which is the biography of Paul Langevin, which, since I have some interest in Langevin, so I read and enjoyed. And she also another biography she's just finished. She's still in print. It's called Biographies of Materials. I guess it will be different kind of biography. And another one, which is in the print, is Living in a Nuclear World from Fukushima to Hiroshima, in collaboration with Surya Budia, yeah, and Kei Sato. I think the number you can find a very long list in our website. I will stop here and leave the floor for your talk, which is what philosopher can learn from chemistry. And thank you very much for accepting our invitation, of course.
Well, thank you, Shaul, for the invitation. I'm sorry to be just on Zoom. I would have liked to talk with all of you, an informal talk after the presentation, but that will be for maybe another year in Jerusalem. And I will try to share my screen now, if I can. It should work. So do you see my screen now? It's okay?
Yeah, now it's fine.
Okay. So why did I choose this topic about the learning from chemistry for philosophy? It's mainly because when I studied philosophy, especially the philosophy of science, I noticed that most 18th century philosophers, 20th century philosophers ignored chemistry. The physics provided the ground for the standard issues discussed in the 20th century philosophy, like laws and causation, confirmation and induction, realism versus positivism, reduction versus emergence. And most philosophers developed comfortable armchair philosophy, while tons of chemicals penetrated and invaded the environment. So they were blind to what was going on in the real world. Even nowadays, when physics is no longer viewed as the wool of science, philosophy remains an exotic, chemistry remains an exotic corner in philosophy departments. It continues to be perceived as a dirty and messy science. Impure science, because of its practical engagement with technological and industrial productions. So it's precisely because chemistry is an impure science, and I take impure in the chemical sense of the meaning, that is something mixed with some other things. Because it's not an ideal pure science, that it's of interest for philosophers. I contend that chemistry is of interest precisely because it is an alternative to the ideal of pure science. It provides a ground for a renewal of the philosophical issues about science and technology. At least if we accept the chemistry, that philosophy of science in the continental tradition of philosophy of science, I mean a philosophy of science which is rooted in the history of science, unlike the analytical tradition of philosophy of science. So what I would like to tell you today is why an impure science can be of interest for philosophers. I will deal with three major aspects. One is more epistemological, is because chemistry is really a science where knowing is gained through making something. So it's the collaboration between knowing and making which is of interest. It's also interesting because of the idea of material agency. And third, because it's based on the view that there are material individualities irreducible to the figure of matter as an homogeneous thing, entity. So let's start with knowing through making. We know that alchemists invented the laboratory. The laboratory is a place, a space, a closed space, investigating nature, which is around. So today, it's the archetype of all experimental science, but it was really initiated by alchemists in the medieval time, and it's of interest because it's a place of labor. Laboratory means a place of labor. It's a place where matter is bring in and it's going to be transformed, and that will tell you something about the world. And so the idea in the laboratory science is mainly based on handbooks of recipes. And it's the trace of the artisanal origins of chemistry, because before becoming a science, chemistry has been mainly a collection of craftships, and it's important to have this in mind. Handbooks of recipes are the first book of chemistry. But it doesn't mean that there is no theoretical ambitions in chemistry. because chemists have always to make conjectures about what's going on in the chemical reaction in the laboratory. And it's the collaboration, the combination of recipes and theoretical ambitions that makes the singularity and the identity of chemistry. And it's interesting because chemistry could have been the model, the archetype for Francis Bacon's famous metaphor of the bees. If you remember, he accepted that those who have treated of the science have been either empirics or dogmatics. The former, like ants, only heap up and use their store. The latter, like spiders, spade out their own webs. The bee, a mean between both, extracts matter from the flowers of the garden. From the flowers of the garden and the field, but works and fashions it by its own effort. So it's really the medium position between the ants who search empirically for the truth and the spiders who prefer to spin out theories. So it's this medium position which is really articulated in the laboratory work of chemists, because it's a mixture of praxis and poiesis. Chemical operations are productive not only of new material substances, there are more than 3,000 new molecules created by chemists every year, but it's also a production of knowledge. And the knowledge is acquired first through a labor of purification. Purification of substances bring new properties of substances. And it's mainly a work conducted through analysis. The composition of substances, that is the nature and quantity of components, is acquired through analytical work, through a number of chemical procedures for analysis, and also today physical procedures of analysis, of course. But analysis is not sufficient to prove anything about the composition of substances. The real proof of the composition of substances comes from synthesis, which is the ultimate proof of the composition, at the same time as it's providing new molecules. And the champion of synthesis, who was Marcelin Berthelot, especially in La Synthèse chimique, published first time in 1860 and then republished in 1876. And it's been a real success book, which has been reedited many times. And he had this famous claim that many chemists have taken for themselves since that, which is chemistry creates its object. This creative faculty, akin to that of art, forms an essential distinction between chemistry and the other natural or historical science. The latter have an object given in advance and independent of the scientist's will and activity. The general relationships that they can discern or establish are based on more or less probable inductions or even on simple conjectures that is impossible to verify beyond the external sphere of observed phenomena. These science do not possess their object. On the contrary, experimental science have the power to realize their conjectures. They pursue the study of natural laws, creating a whole set of artificial phenomena, which are their logical consequences. In this respect, the procedure of the experimental science is not without analogy with that of mathematical science. So this is why chemistry is the model of experimental science for Berthelot, because, and it's also akin to mathematical reasoning, because really it really performed the proof, it realized the conjecture, while the mathematician's reasoning based on abstract data and established by definition leads to conclusions that are both abstract and rigorous. The experimental's reasoning based on real data, which are always imperfectly known, leads to factual conclusions that are never certain but only probable, and so can never dispense with effective verification. So for Berthelot, what is important in chemistry? It's really not that it has the power to create new objects. He was much more interested in the cognitive power of synthesis. And the cognitive power of synthesis is really a predictive power. And he gave as an example Adolf Wurtz's prediction, although Adolf Wurtz was his enemy on a theoretical ground, because Adolf Wurtz advocated the atomist theory that Berthelot rejected. Nevertheless, he really admired Wurtz's prediction of the existence of an intermediate diatomic type of compounds, which would take place between the ordinary monoatomic alcohols, like ethanol, and the three atomic ones, like glycerin, and that for this reason, Wurtz named glycols or glycols. So he compared them to the prediction by the astronomer Le Verrier of the planet Neptune, which was calculated before it was observed. And it's the same for the glycol series of compounds, because they were predicted before being realized and observed. So it's really this combination of prediction and realization, which is the hardcore of chemistry. Synthesis is also, of course, for Berthelot, a promise of plenty, a cornucopia of everything. Chemistry, he added, possesses this creative faculty to a higher degree than any other science, because it penetrates deeper, attaining the nature of elements of things. I'm not going to read everything, but what is interesting in it is that the artificial entities are, for him, instantiated images of abstract laws that chemistry seeks to know, without leaving the sphere of legitimate ambition. We can hope to conceive the general type of all possible substances and create them. We can, I claim, hope to recreate all the substances that have been developed since the very beginning and form them in the same conditions, according to the same laws, using the same forces that nature put into effect to do so. So in mimicking nature through synthesis, chemistry is doomed to replay the creation of nature by God. And the idea is that chemists have the power in their labs to recreate nature, to redo the genesis of nature. So it's really, they really assume the mission of playing God. And it's assumed for technological reason and cognitive reason. So for Berthelot, really, it's genesis rather than molecular structure which gives access to the nature of compounds. That's why Berthelot strongly opposed the atomic theory, He opposed the atomic theory because he didn't believe that molecular structures could provide anything of interest for chemists. For him, what made the real nature of a chemical, its genesis, how you access to it. That's why he wrote the formula of benzene, CH2, 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 3 times CH2, because he synthesized it through the combination of acetylene. And for Gaston Bachelard, the French philosopher who really admired Berthelot, chemistry was defined as a science of effects, moving from fictions to facts. Fictions are the conjectures, and moving from fictions to facts, that's the typical epistemology of chemistry. Chemical synthesis is a process of realization, of penetration of reality by human reason through instrument what Gaston Bachelard called phenomenotechnique. Phenomenotechnique is how you create phenomena through technological instruments. And this is what Gaston Bachelard called rational materialism. So it's division of synthesis as a rational materialism that was promoted by Marcelin Berthelot and Gaston Bachelard. And for them, chemistry was a rational materialist science. And Bachelard wrote the rational materialism. And in my view, chemistry is much more not rational materialism, because it accepts irrationals. It's more a pragmatist materialism, because the priority is action. So chemists are playing God. They are playing God, sure, but playing God in the sense that Giambattista Vico, the author of Scienza Nuova, in the 18th century, gave to this term because verum et factum convertuntur, meaning that truth and making are reciprocal. You can get truth only through making. You can know truth only through making. That's why Giambattista Vico has been considered as the early modern constructivist approach to truth. But at the same time, it was for him the key argument to claim that only God, the creator of nature, could know nature and understand it, because you know only through making. And in a sense, this is the wage of chemists. It's they can know nature through making it, remaking it in the closed space of the laboratory. And this is this continuous effort of chemists until today, in the 21st century, to make artificial life or synthetic biology, which is mainly in the hands of chemists today. That is really their identity in the philosophy of to reach truth through making. So let me now turn to the second aspect, their view of matter as material agencies, something that, in my view, is characteristic of a new form of realism, which I call agential realism. Bachelard, again, in 1940, wrote The Philosophy of No, La Philosophie du Non. And this Philosophie du Non is, I'm trying to get my quotations, okay. Metaphysics, he contrasted metaphysics and metachemistry. Metaphysics could have only one possible notion of substance, because the elementary conception of physical phenomena was content to study a geometrical solid characterized by general properties. Metachemistry will benefit by the chemical knowledge of various substantial activities. It will also benefit by the fact that true chemical substances are the products of technique rather than bodies found in reality. This is as much as to show that the real in chemistry is a realization. It's this idea that chemistry constructs a real, it's really a constructive philosophy. And this idea of a constructive philosophy, it's blocked. My slides are blocked now.
Right.
For some reason. So I will stop to share and try to get it again, to get a hand on it. And then I will share again. No, it's blocked.
Okay.
Well, do you see it now?
Yeah, no,
Okay, so I try to get to the next one. So the major aspect of chemistry.
Please move to the presentation view. Yeah, thanks.
I hope that it will, yeah, it will work. So the major point about chemistry is that it's an anti-Cartesian science. Why? Because for chemistry and metaphysics, in Bachelor's term, the matter is just homogeneous matter, deprived of inequality. Whereas the chemist is not interested in matter. The chemists are interested in heterogeneous materials with specific individual qualities. And also for Descartes, matter is passive, it's deprived of activity because it's pure spatial extension. But for chemists, materials, substances are active and reactive. They are continuously reacting in the laboratory. And this is why they are interesting. And the Cartesian view of matter was the foundation of a typical mechanicism, which is a passive mechanicism. Whereas chemistry needs mechanicism, but it's a dynamic mechanicism where materials do something. Materials are not defined just by their structure and composition. They are defined by what they do, but how they behave and react on other materials. So we have two mechanicist traditions. The Cartesian mechanism, it's about passive and inert matter, whereas chemists are more keen to Newtonian mechanism, attracting and repulsing particles. Whereas in Cartesian mechanism, substances are defined by their inert mass. In chemistry and Newtonian tradition, substances are defined by their relations. And whereas in Cartesian mechanism, all agency is located in God, the clockmaker. In the dynamic tradition of mechanicism, agency is located in material corpuscles. That's why the chemists drew a lot and learned a lot from Newton's famous query 31 in his optics. If you remember, his point was, it seems to me, Father, that these particles have not only a vis inertiae accompanied with such passive laws of motion as naturally result from the force, but also that they are moved by certain active principles, such as if that of gravity, and that which causes fermentation and the cohesion of bodies. This principle I consider not as occult qualities, supposed to result from the specific form of things, but as general laws of nature, by which the things themselves are formed. Their truths appearing to us by phenomena through their causes be not yet discovered. For these are manifest qualities, and their causes only are occult. So this is really the basis of the philosophy of chemistry. Qualitative, and it was the robust basis for the table des rapports, the affinity tables that were promoted in the early 18th century at the Paris Academy of Science. These table des rapports are really a qualitative measurement of the attractive forces between substances, these attractive and repulsive forms that Newton conjectured. And so it was also a productive tool based on hundreds of chemical reactions, which provided really the equivalent of the Mendeleev's table of elements in this time. So how do chemists deal with occult forces? Because the forces are factual, but their causes are occult. So how to deal with them? Are they going to have something to promote something like the mysterious vital force? What is interesting is precisely that Thomas Huxley, a 19th century philosopher and of biology, used chemistry as a model to avoid the trap of the vital force. In his lecture, promoted in 1868, The Physical Basis of Life, he really called chemistry as a model to avoid the notion of vital force. We do not assume that a something called aquosity entered into and took possession of the oxide of hydrogen as soon as it was formed, and then guided the aqueous particles to their places. On the contrary, chemists or we live in the hope and in the faith that by the advance of molecular physics, we shall by and by be able to see our way as clearly from the constituents of water to the properties of water as we are now able to deduce the operation of a watch from the form of its parts and the matter in which they are put together. So chemistry really is the model of a dynamic tradition where you can predict and you can understand the behavior of substances without calling for a metaphysical entity called aquosity or vital force. You simply accept that there is something occult and that this something occult will be one day, in principle, in our reach, in our understanding. So this is this kind of rational, reasonable phase that is typical of the dynamic mechanism of chemistry. They accept that they will one day understand. So this occult force has been really understood. The occult forces have turned into chemical bonds. Chemical bonds are the equivalent of the Newtonian occult forces, but they are still considered today, they still retain something occult. And I would like to draw your attention to the splendid lecture delivered by chemist Richard Smalley for the discovery of the fullerenes. You know, these allotropes of carbon, and how Smalley depicted his discovery of fullerenes. He talked about carbon genius. The discovery that garnered the Nobel Prize was the realization that carbon makes the truncated icosahedral molecule and larger geodesic cages all by itself. Carbon has wired within it as part of its birthright. Ever since the beginning of this universe, the genius for spontaneously assembling into fullerenes. So this is really this spontaneous activity of molecules, of atoms and molecules, and through the capacity of carbon atom to make bonds with nearly all other elements, but also with itself, with all other carbon atoms. That is the genius of carbon. And this real genius, which is something like a demon, you know, is really what is the view of the chemical view of matter. Matter is active. Matter has something occult in it, which is active and that allows the self-assembly of atoms into molecules and the self-assembly of molecules into supramolecules. This is why self-assembly is the basis of supramolecular chemistry. As Jean-Marie Lehn, who pioneered supramolecular chemistry, realized supramolecular chemistry is based on the lock and key model. The lock and key model that has been invented in the late 19th century and is now the basis of all supramolecular chemistry and nanotechnology as well. There are two conditions for self-assembly according to supramolecular chemists. First, the reversibility of the assembling parts, meaning that they rely not on covalent bonds, which are strong bonds, but they rely on hydrogen bonds or electrostatic or ionic bonds and labile interactions like hydrophobic and hydrophilic interactions. And the second condition is that information has to be encoded in the components rather than provided by a designer, an external designer, or an external program like the genetic code. It's not provided by the designer or the clockmaker. Neither is it provided by the genetic code. It's embedded in the molecules. And this is this capacity of bonding, which is embedded in the molecules and the atoms, that is the reason for the specific philosophy of matter and chemistry. Oh, it's again, I have to go back. It's again.
We'll wait again.
Yeah. So I will stop again, go back here. So I will check. Can you see it? No?
No.
Okay. So I have to share it again. I'm sorry for this inconvenience. That's the problem of being far from you. Well, now you can see.
One we can see. Yeah.
Okay, I hope I don't have to do that at all slides, for all slides. So the philosophical implication is that chemistry is really questioning a typical classical philosophical dichotomy, the dichotomy between subject and object. Why? Because in the traditional subject-object dichotomy, design is the production of an object is the realization of the designer's project or plan. And only the subject is active and it's facing a passive matter. This is what we call in the jargon the hylomorphic model. I mean, the artisan, or elaborated by Aristotle, the artisan imposing his plan, his the eidos on the passive matter. And in the traditional dichotomy philosophy, the artifact, the product, is the expression of the designer's creativity, like in artistic design. Whereas in chemistry, the design of new molecules is rather like monitoring material dispositions. And the chemists are not really operating transformations of matter. They harness the power of selective material elements. They are monitoring, or they are guiding the power embedded in the capacities embedded in matter. So to a certain extent, the product, the artifact, is a co-production of the chemist and of materials. And it's a quite different philosophy than the classical philosophy generated by metaphysics, classical metaphysics. So now let me turn to the third aspect. Chemistry is assuming multiple individualities, or what I call ontological pluralism. There are two types of pluralism in chemistry. First, they assume a diversity of chemical entities, of chemical elements, not just one matter, but a diversity of chemical elements. And second, there are a variety of modes of existence of these elements and of chemicals. First, the diversity of chemical entities. This is really important because we have to, and I would like to emphasize the complexity of the notion of chemical element. And for this, I will start from this strong commitment to pluralism that was really formulated by Dmitry Mendeleev when he designed the periodic table of elements. And in his Faraday lecture in 1886, he said this: Kant believed that there were two objects in the universe that provoke the admiration and veneration of man: the moral law within us and the stellar heavens above us. And further exploring the nature of the elements, we need to add a third such object, the nature of the elemental individuals that is expressed all around us, in light of the fact that without these individuals, we would be unable even to form an idea of the stellar heavens, and that furthermore, the notion of these atoms reveals the singularity of their individuality, the infinite repetition of these individuals, and their subordination to the harmonious order of nature. So this is a bit grandiloquent and pompous, but the idea that there is an irreducible plurality of elements is key to understand the philosophy of chemistry. And this is important because the notion of chemical elements has nothing, no, it's not that it has nothing, but it's different from Lavoisier's definition of elements. Lavoisier, if you remember, defined elements as simple substances. If we apply the term elements of principle of bodies to express our idea of the last point which analysis is capable of reaching, we must admit as much elements all the substances into which we are able to reduce bodies by decomposition. So for Lavoisier, elements were defined only negatively as undecompounded bodies. They were and Lavoisier deprived the elements of all positive features. That's why his concept had a weak explanatory power. It couldn't explain the individual behaviors of chemical substances. This is what I call the compositional paradigm of chemistry. And Mendeleev, to construct the periodic table of elements, had to introduce a distinction between simple body and elements. A simple body, a substance, as we already know, is a substance which is taken individually, cannot be altered chemically by any means produced until now or be formed through the transformation of any other kinds of bodies, which was more or less a more complex definition of simple substances. An element, on the other hand, is an abstract concept. It is the material that is contained in a simple body and that can, without any change in weight, be converted into all bodies that can be obtained from simple body. So the definition, the distinction introduced by Mendeleev is important. Oh my goodness, again, I'm stuck. Maybe if I keep this presentation, can you see now?
We can see it for smaller, but
yeah.
Is also
but it's when I turn to full screen that I'm stuck.
But change the zoom to full that it would include to full window or something like that. Okay, no.
Okay, I will try to do that. Okay, so the element is a strange concept. Chemical element is a very strange concept because it's a material abstraction. It sounds like an oxymoron, you know. It's abstract because, unlike simple bodies, elements are nowhere to be seen or touched. They are not the concrete residue of analysis. It's different. They circulate through chemical change reactions. They are conserved, but they are not, you cannot see them, you cannot touch them. They have no concrete existence. But they are material. They are material because they can be weighed and individualized by their atomic weights. So they are more than the result of an intellectual process of abstraction. They are really acting, operating on other elements because they have a transformative power. And this is why Mendeleev really insisted on the difference between a simple body and a chemical element. The chemical element assumes the function of conservation of matter, but it's a conservation of matter not only through Lavoisier's law of conservation of matter, it's a conservation of the properties of individual properties. And this conservation of individual properties, he placed it in the atomic weight. The atomic weight belongs not to coal or diamond, but to carbon. And carbon is really the archetype of the distinction between simple body and a chemical element, because there are many allotropes of carbon. So elements, chemical elements are always on the move. And you cannot take them in your hands. You cannot size them. You cannot see them. As John Early mentioned in a provocative paper published in the 1990s, there is no salt in the sea. There is no salt in the sea because there is no real salt. What you have in the dissolution in the sea, in the water of the sea, it's ions, ions of sodium and ions of chlorine. But there is no salt. And there is no sodium and no chlorine in table salt. No? Because there is no soft metal like sodium, nothing like a soft metal in table salt, and nothing like a greenish gas like chlorine and toxic gas like chlorine. You can eat salt. So this has been pointed out by Emil Meyerson, who was a chemist and a philosopher. And Emil Meyerson really insisted that because there is no sodium and no chlorine in table salt, chemical equations are a nonsense. Chemical equations are a nonsense because sodium plus chlorine equals sodium chloride is a nonsense, because there is no, this is the limitation of Lavoisier's compositional paradigm. It doesn't make sense, even if you change the sign equal with the arrow like we do today, it doesn't make sense. The compositional paradigm is uninteresting for chemists, because if chemists try to combine sodium and chlorine, it's precisely because they want to get something different. And the interest is really that you have to get something different. Although elements are conserved and can be retrieved according to the principle of conservation, they disappear and something different happens. So there is a real emergence in chemical reactions. There is a real emergence without any vital force, without any genetic code. There is emergence in chemistry. There is emergence, and this emergence comes from the capacity of matter. So beyond the conservation of mass in chemical reactions, elements are individual and multifaceted entities. And let me take carbon as an example of the multiple identities of chemical elements and materials in general. Carbon has many allotropes. Diamond has nothing to do with graphite. And with all the nanotubes, fullerenes, and graphene, which is the last baby of the long list of carbon allotropes. And carbon has many, many compounds because of the capacity of carbon atoms to make link bonds with most of other elements and also with carbon atoms. Carbon is the basis of DNA. There are hydrocarbons. Carbon is also the basis of CO2. Carbon is the basis of oil and coal. So there are many, many modes of existence of carbon. And the carbon multiple modes of existence are really what makes chemistry interesting. And carbon is the ideal type of these multiple modes of existence of chemicals, because you have the chemical mode of existence, the carbon element. But carbon element is also different from the tetrahedron of carbon atom, because element and atom are different. But there are also a geological mode of existence of carbon. Carbon exists in rocks. And as Primo Levi nicely described in the last chapter of his fiction, the autobiographical fiction called Entitled The Periodic Table, the Periodic System, carbon lies for many, many millions of years in rocks before it starts moving in its biological mode of existence, where it circulates. And it circulates through the cycle, the geological and biological cycle of carbon in the atmosphere. And it also has a societal mode of existence, because it exists in industry, and it has to be, the carbon has to be stored and stocked in carbon sinks today for ecological reasons. It also exists in an industrial mode of existence through all the plastics that are spread all around the markets and that end up in the ocean as plastic debris today. So the idea of the multiple modes of existence of carbon is typical, and of materials is what precisely chemists can bring to philosophy, the idea that something can have multiple modes of existence. So chemistry really leads to questioning the traditional notion of substances. A substance is not something that is just conserved. It's not just something that is underneath. Beyond structure, the sequence structure to properties, chemical entities are defined by their interactions with other chemicals and also with their environment. The properties of sodium change according to the neighbor atoms or molecules, as do the molecules of water. They change in a glass of water. It's not according to so it's a relational ontology. I mean, the identity of materials is defined by their relation to other materials. And this really undermines the traditional distinction between substantia, what it is, and potentia, what it can be, or what it can do, what it can become. Because the chemicals are defined by not only their dispositions. Dispositions are inherent into chemicals. They are intrinsic to the chemicals, but they are also defined by their affordances. And I take the term affordances, which has been coined by a psychologist, but it has been redefined by Rom Arey to refer to the complex of activity that is inspired, that is formed by a substance and the apparatus. He took the example of metallic sodium. Metallic sodium came into existence through the electrolytic apparatus of Humphrey Davy. So it came into existence, it came into being as the result of the encounter between the intrinsic potential of sodium atoms and the apparatus. So affordance manifests both the dispositions of atoms and of the milieu, the environment or the world apparatus. So this is the specific message of chemists for the ontology of matter. So it's also another aspect is that it's also challenging the nature-society divide, which is also the basis of Western philosophy. The nature-society divide relies on the idea that you have on one side natural determinism or natural causality, and on the other side you have the conventions of society. You have the laws of nature and the laws of right, which are completely separated. But if you look at chemicals, materials in general, there are hybrids of nature and society. Chemical molecules do not come into being out of necessity. They come into being under technical and economic pressures. And like plastics, for instance, or like nanotubes today. They are created for economic reasons and societal demands. So chemical elements have a social life in technological objects and commodities. They have a market life. They have a political life, especially in colonial history. Chemical elements and minerals really were one main driver for the colonization of countries, and they are still a major driver of geopolitical tensions, especially the geopolicy of China today in Africa, for instance. And they also have an environmental impact because of the extraction of minerals and because of waste of chemicals that are polluting the environment. So there are many, many modes of existence of chemicals that make them challenging the nature society or nature culture divide. And I would like to end up this presentation on the recent periodic table published by the European Chemical Society. Because you see in this periodic table, which is unusual presentation, They really consider chemical elements as hybrids of technology and nature, and technology. So it also challenges the divide between natural and artificial, between nature and technology. Because in this periodic table, the elements are placed, located, and colored according to their uses, technological uses today. So you see that there is a real threat on a number of elements which are becoming critical, mainly the elements that are used in electronic technology today, and that are becoming critical, and which are in near extension today. So to sum up, what lessons we can learn from chemistry? I mean, we can mainly learn that philosophy has to be open to the world around us. And I think that the epistemic profile of chemistry, it's a science open to the unknown. It's a science open to in an exploratory attitude, and which is open to the unknown, even to the occult or provisionally occult, and that can be one day explained. And it's also a technoscience. And what I mean by technoscience, it's not only that it's interweaving science and technology, but it's also that it's sensitive to societal and economic demands or pressures. And the metaphysical profile of chemistry requires a new specific ontological categories. Categories like disposition, of course, it's not a new category, but it's redefined. Affordances, a relational ontology, as opposed to the classical essentialist ontology of Western modern philosophy. So, as an alternative to ideal pure science, because of its impurity, chemistry can teach many, many things to philosophers. Thank you for your attention, and I'm sorry for the disaster with the slides, but I will wait for your questions.
Thank you very much, Professor Bensaude-Vincent. And now we can have questions. So please, the floor is open, and please also turn on your cameras now, because we can see you now more. Bernadette, do you have a question?
Sorry, actually, I didn't, but now that you asked me, I might just pose one, if that's okay. May I ask you to go to the slide, if it's possible to go back to the slides? Actually, you were talking about meta chemistry, in a position to metaphysics, and I like that a lot. But may I see the slide again to be able to pose my question?
Yeah, I have to share the screen again.
Yeah, if that's possible.
I'll be back to. So you have it. Metachemistry.
But there was another one about metachemistry, no? Or is it that?
Is this?
Or maybe the one before that. Yeah, maybe you were right. The other one.
No, it's this one. The metachemistry was this one.
That one. Because I was for a while having this idea that that in physics maybe objects should also be defined by how they are produced, how you can like make them in experiments, rather than just having this abstract notion of them. And this, what you say here about metachemistry and about like, this resonates a bit with the idea that I had. And so I was wondering if you maybe had something similar in mind there, that one thing that maybe philosophers of physics or even physicists could learn from chemistry is this, that they should see the objects that they treat not so idealistic, but more practical in terms of how they create them actually, how they manage to produce them, and that this is actually part of the object of the definition of the object. Do you know what I mean?
Yeah, I think, thank you. You are perfectly right. This is to a certain extent not specific to chemistry, because in philosophy of physics, you can say that you define electrons because you get them on the screen because you by your action you can define electrons, and this is what Ian Hacking explained, if I remember well, in representing and intervening. Remember that it's through your intervention on reality that you can believe that electrons exist. You believe that they exist precisely because you can move them, you can intervene on them. And it's through your action that you can make them real. So this is partly common to physics in the sense that physics is also an experimental science. So it's not specific, but I took chemistry because chemistry was really the cradle of experimental science historically. But you are right. And that's why it's the same in biology today. You can also create living entities in the laboratory and intervene, and they are real because you make them.
Questions? So I would have one. You can think of others in the meantime. So my question, you mentioned the metaphor of the watch, of the clock, that we can know how the water, the properties of water, as we know from the basic properties of the chemical, from the basic knowledge of the chemical elements. So it doesn't this kind of metaphor put in mechanism in the non-dynamical sense? Because if we think of the watch, usually that's the metaphor, that's the Cartesian metaphor, although it has all the roots already in the 14th century. So if we think about this, it goes more into an ideal of a mechanical ideal also for chemistry, and in a sense you can say that quantum equations for the covalent bond are kind of not exactly mechanistic in the Cartesian way, but also not totally dynamic as Newtonian.
Yeah, I think the clock metaphor is interesting because to a certain extent it can be ambivalent, you know. I refer here to the book by Jessica Riskin, which is what is called, it's The Restless Clock. And what she argued that there are two traditions of mechanicism. the passive mechanicism and the active mechanicism, and the dynamic dynamic as opposed to static. And she refers mainly to Leibniz as the countermodel of the Cartesian clock. For Leibniz, the clock, of course, there is a clockmaker, but the clock is restless. It's continuously active and reshaping itself. And she identifies a long tradition that goes back to Leibniz, then to Diderot, La Métrie, which is a materialist tradition, but an active materialism, a dynamic materialism, and a mechanicism. So, like most metaphors, the clock metaphor can be ambivalent, of course. But I would say that sure, the bonds, the chemical bonds, are a form of dynamic mechanicism. And so it's mechanicism, of course, it's quantum mechanics, but it's a dynamic mechanism because there is always this activity inherent in matter.
Yes, Ilona Sidor, please. We don't hear you.
Mute. Okay. Could you please elaborate a little bit more about the philosophy of chemical synthesis?
Yeah.
And I heard your lecture in Paris a few years ago in the conference of the Philosophy of Chemistry International Group. So please.
Well, the philosophy of synthesis, it's really the core of the singularity of chemistry, and there are two views of synthesis, I would say. The one view of synthesis is the one that I presented, elaborated by Berthelot and by Bachelard. I mean, it's a view of synthesis as the realization or concretization of rationality, of the rationality of human subjects. And there is an alternative view of synthesis, which is much closer to what chemists are actually doing. And I would refer especially to the view of synthesis elaborated by Nobel Prize Rod Hoffman in a famous article in praise of chemical synthesis, which was published in the 1990s, if I remember well. And he really compared synthesis to a kind of musical composition, an artistic composition, playing, with tonalities and playing, and it's an art. And he compared it also with the chess game with nature. It's really playing a chess with nature capациties. And you are not always the winner, because sometimes the nature plays tricks to you, and the chemicals play tricks to you. So that's a different view of synthesis, which is what I call the pragmatist view of synthesis, or the pragmatist realism.
Thank you very much. I want to mention, you mentioned affordance by Ron Hare, a colleague of mine, a Japanese fellow, Ochiai Hirofumi, wrote an article about that. Maybe you've noticed it.
Yeah, I don't know this article. If you can send me the link. Thank you.
Okay, I will, please.
Thank you.
Thank you.
Maya, please.
Hi. Yes. Thank you very much. It was very interesting talk, and we don't get a lot of philosophy of chemistry, so I thought it was a very interesting addition. I'm interested because a lot of the points you touch on, like changing the dichotomy between subject and object and seeing science as a form of art, are raised by feminist philosophers of science as aspects of feminist science that should be adopted by other sciences. And I teach a class on feminist philosophy of science, and whenever we get to feminist philosophy of chemistry, I'm not sure what is the status there. So I'm wondering if you have any thoughts, if it's of any interest to you, or if there's been any impact of feminist thought on philosophy in the field or on the practice, or any thoughts on gender and how it relates to the work in the field. Just thank you.
Yeah, thank you for your question. Of course, there is a link. And I would say that it's chemistry who drove me from the philosophy of chemistry to my interest in ecofeminism, I would say, rather than feminist. It's ecofeminist literature. And it's true that the books like Vibrant Matter or things like that are very, very close to the chemical philosophy that I try to outline in this lecture. And curiously, there were historically very few famous woman chemists, apart Marie Curie, of course, which is always the archetype. But I contend that chemistry is really of interest and has been always of interest for women. If you look at in the 18th century, the people who attended the very popular chemistry lectures in Paris, London, everywhere, they were mainly women, and some of them wrote chemical books, which are now rediscovered by a number of PhD students because today women scientists are fashionable. So it's a real rediscovery that chemistry is a feminine science to a certain extent, because women working at home had to make their own chemicals in the past. They had to make their own products, and that's still the case. It's coming back today. So there is probably a female dimension of chemistry that attracted me, maybe, but it's more rapid psychoanalysis. I don't know. It's not really serious when I say that. Thank you.
Ori?
I think I'm going to ask the question this way. Actually, dynamic mechanical models go back all the way to Francis Bacon. And he was actually very much influenced by alchemical theories. And he had his own alchemical theory, which he endorsed. And his scientific method, his experimentalism, and his idea of what induction means is actually influenced by this dynamic mechanist model of nature. So I think I can ask my question this way. On the one hand, experimentalism seems to push us into the direction of something like recipes. It's some way in which we intervene in nature. And it's more about the intervention in nature and influencing substances and transforming them than in theoretically understanding the underlying processes and so forth. So I think that comes out very strongly in your presentation, that there's an element of human intervention or human action, human technology, which has to be explored in order to understand these objects, these chemical objects. But on the other hand, if you think about dynamic mechanist models, they do have a theoretical underpinning, always. There's always something about what nature is like and what forces it exhibits. It's true for Bacon, and it's true for Newton, and it's true for any kind of dynamic mechanism that was put forward, that there is a theoretical framework that actually allows us to guess how I might intervene in nature and how I might create new substances, given what I know about these natural processes. So how do you understand the relationship between the theoretical aspect and the experimental aspect?
Well, I'm glad that you mentioned Bacon as an alchemist. Yes. Because, yeah, and I think this is really overlooked. And I think it's very important to point the role of chemistry, as they used to call it, chemistry at that time, in the what is called the scientific revolution, or the emergence of modern science, modern experimental science. You are perfectly right that Bacon was probably strongly inspired by his alchemical experimentations. But now, concerning the link between the theoretical framework and the practical interventions, I think that the function of theories in chemistry are not the same as they are in physics. It's less explanatory, I would say. It's more narrative. It's making up a story to understand what is going on in what you cannot see in the black box of the chemical reactions. So it's constructing a narrative, a plausible narrative of what's going on. And if possible, to construct a plausible narrative that allows you to predict what will happen the next step. So it's I would say it's more narrative than explanatory, in the sense of bringing the ultimate cause of what happens. I don't know if it answers your question, but I think it's the functions of theory. They need theoretical theory, of course, and they need models today also. And there are many models, but the theory is not simply derived from experiment. It's also instructing experiment through this kind of narrative built up by the chemist, the theoretical chemist. Are there any chemists in the audience? That would be interesting to see their reactions.
I'm a chemist.
You are a chemist.
I now is turned to be historian of chemistry of Japan. And I cited your article about language in chemistry in my new article about translating Roscoe chemistry book into Japanese in 1873 and into Hebrew in 1929. And I look at the difference in history, in culture, and language between those two translations. Just the experiment of Roscoe describes of the burning candle.
Yeah.
I'm afraid we have one more question, but I'm afraid we need to close now because it's a little bit late and we have run out of our time. So that will have to wait for another occasion. So thank you very much for.
There is a question by Juan Camillo.
You can do it. Juan.
And another one by Shira.
Yeah, please.
Thank you, Bernadette, for your talk. Always really interesting to hear you. It seems to me that philosophy of chemistry established itself as a separate field from philosophy of science recently. Thank you to the debate of reduction, no? How molecular chemistry is related to quantum mechanics. I really would like to know your thoughts about this debate about reduction, the relationship between chemistry and quantum mechanics.
Yeah, this my answer will be short. I'm not interested at all in reduction issues. I know that this issue of reduction was crucial for the emergence of the philosophy of chemistry in the late 20th century as a discipline, especially through the journal Foundations of Chemistry, edited by Eric Scarry. And in the beginning of this journal, it was the major issue discussed. Now it has changed. But personally, I'm not interested at all in this issue of reduction. I don't think it deserves any more comments.
Thank you so much.
That's no comment that we will. But we had a lot of things that deserve your comments before. So thank you very much for the rich talk, Professor Bernadette Bensaude-Vincent, and thank you for the audience. Next week, we will intervene as usual here in the room for our seminar. Thank you very much.
Thank you to you, and thank you for your participation. Bye.
Bye-bye. Thank you.